G'day guys, we've got a applications of differentiation question today where we've been given a function q of t is equal to 100t e to the t. We've got to find the exact value of the instantaneous rate of change. The exact value of t when the instantaneous rate of change is 0 and the exact local minimum for q. Okay, well let's go about this. Now, if we see this instantaneous rate of change, that means we have to differentiate. This should be like one of those things in your head where it just clicks. If you see this in the exam, it means you have to differentiate. So let's start by, without looking at anything else, let's start by differentiating this. So we're going to have dq dt, and because we've got f of x and g of x, we've got two functions multiplying by each other. We've got a linear and we've got an exponential. So what we're going to do is we're just going to go the derivative of the first one times the second one, add, we leave the first function constant, and we times it by the derivative of the second, which is itself. Cool. So there is our derivative. Now we have to find the exact value of the instantaneous rate of change of q with respect to t when t equals 1. All right. So then on the next line, so this is A. So in the next line, we're going to get dq dt evaluated when t equals 1 is equal to 100 times e to the 1, which is just going to be 100e, plus 100 times 1, which is just 100, e to the 1, which is just e, which simplifies down to 200e. Cool, so that's our solution for part 1 of the question. Let's move on to part 2. Okay, so B. The exact value of t when the instantaneous rate of change of q with respect to t is 0. Okay, so we have this dq dt function. This one here's a little bit more tricky than the first one. So what we can do with this is, if we're looking for something to equal 0, we want this to equal 0. Now, if you have a function that has, well, it looks a lot like this. If you've got multiple things and they've got to equal 0, the best way to do it is to factorize it so you can take advantage of what's called the Null Factor Law. Now, let's factor, so we'll show you how that would work in this function. Let's factorize this. So it has a common factor of 100e to the t. Now that's going to be factorized. We're going to, inside a bracket, we can have 1 plus t. Now we're trying to make that equal to 0. Now the null factor law states that if we've got two things that are multiplying by each other that equal 0, at least one of them has to equal 0. So what that means is either 100e to the t is going to be equal to 0, or 1 plus t is going to have to equal 0. Now, you can see for yourself, but 100 times e to the power of t, there is no value of t which is going to make this function here, this part of the function, equal to 0. So we can write that down if you like. 100e to the t equaling 0. Well, that does not exist. But we know that if we want to have 1, this is quite easy, 1 plus t equaling 0. It's quite easy to see that t will have to equal -1. So you can see that for this function to equal 0, t has to equal, you guessed it, -1. Great. Now for the tricky part, well, sort of tricky part of our 3 parts here. Part C. Now, it says the exact local minimum for Q. So a minimum is going to occur when the rate of change of Q with respect to T is equal to 0. So now this question has been really nice to us and has given us the question prior we've worked out what the value of T is when the derivative of the function is equal to 0. So we have this. Now what we have to do is we have to check that it's a minimum. Now there are lots of different ways you can check. You can check the slope either side of this. Like you can have a look at the slope at t equals -1.5 and -0.5 and see if the slope is going down on one side and up on the other. Or you can take the second derivative of this function. Okay, so we're going to do the way I would solve this is I would use a second derivative test to look at the concavity of the function. So what we're going to do is we're going to find the second derivative of this function. So we're going to go d squared q divided by dt squared. So the second derivative, we're going to differentiate this function here. So the derivative of 100e to the t is simply, you guessed it, 100e to the t. And then we're going to differentiate this. Now this is exactly what we had in the first function, 100t e to the t. So the derivative of this is going to be this. So we're going to have this plus 100e to the t plus 100t e to the t. Cool. Which will simplify down to 200 e to the t plus 100 t e to the t. Cool. So what we're going to do is we're going to evaluate the second derivative when at this turning point which we've found, or point here, which we know that the derivative is equal to 0. So what we're going to do is we're going to evaluate the second derivative, or d squared q over a dt squared, and we're going to evaluate that when t is equal to -1. And this is going to be 200 e to the -1 plus, well, it's not going to be plus, is it? Because it's 100 times -1, which is -100. So this is going to be minus 100 e to the -1, which we can write as, because these are negatives, so you can put them in the denominators. Cool. And what we can see is 200 over e minus 100 over e is equal to 100 over e, which is greater than 0. So because the second derivative is greater than 0, this means that q with respect to t is concave up at t equals -1. So concave up, if we just draw it up here, is when the function looks like this. So this is it's concave up. So if we have a point on on a domain that's concave up, that point there is going to be a minimum. So we can write, therefore, the minimum is going to be equal to, the exact local minimum for Q. So we have to then go, we know that T is -1, we just have to figure out what Q is. So Q is going to be equal to, we have to find Q at -1 is equal to -100 times e to the -1, which is equal to -100 over e. Now I'm running out of space here, so let me just clear off this little bit of working out. So we'll just write our final answer on this, and we'll have we can then write, therefore, local min at t equals -1, Q equals -100 over E. And that's our final answer. So you can see that basically all three of these parts of this question require you to manipulate first and second order derivatives. So my advice to anyone trying to complete these is get really, really good at moving between the function, its derivative, and its second derivative, just so you can seamlessly work through it and understand that this instantaneous rate of change is asking you to find the derivative. So I hope this video helped. It's not too hard once you get a hang on being able to calculate derivatives quite easily, but I hope this video helped or contributed to your understanding, and I'll see you again next time.